Okay guys, this is Yo Soy Bimbo Bob, and I decided, hey, now that I got Verilog running, why don't I write some Verilog and then simulate it? And so what I've got up is a block diagram of what I'm going to write in Verilog. Basically what it is the in clock and the din clock are normal things that you think when you're in digital land. They're levels, so the clock goes up and then it goes down, and then the din is changing on every rising edge of in clock. And I have an encoder, and what that encoder is going to do is every time in clock changes, encoded clock is going to pulse. So that means it's going to send a pulse when in clock goes high. It's going to have a pulse when in clock goes low. And the same with the encoded data for din. What's going to happen is anytime din changes, encoder data is going to pulse and do it. And it's going to do this on a per bit basis. So din is multi-widths, and the code is actually written to be variable width. But I'm going to, when I implement it and design it, I'm going to show it as 4 bits. Then I'm going to send that across to the decoder, and the decoder is going to take in those pulses and convert them back to levels. And hopefully it'll be done in such a way that out clock rises and D out changes, and D out either changes at the same time or slightly before out clock rises. And I'm gonna do something interesting, and you'll see why I'm gonna do this later, is basically I'm not gonna use all the values that are available on din. I'm going to only use the values that are all non-zero. And the reason that I'm gonna do that is that enables me to sort of decouple encoder from decoder, and it helps me determine of these pulses that are coming down from in clock, 2 for each cycle of the clock. I can determine which one is the rising edge and which one is the falling edge. And the way I determine that is I look at the encoded data coming in, and whenever I'm on a half cycle that shows me non-zero data, I know, hey, that happened on the first half cycle. I then delete it on the next encoder clock block. And so what that does is it gives me an encoder and a decoder where they auto-synchronize. All right, and so let's show the code that's associated with that. So here I have code, and just as an explanation, hey, if you're a logic designer and all this type of stuff, it is always easier to do stuff with hierarchy. It allows you to reuse code for simple things. And you hear some of the primitives that I have here is an inverter, which basically inverts. I have an observer, which basically an observer looks at a signal, and whenever the signal changes, it pulses. I have something that's called a T-latch or a toggle latch. The way the toggle latch works is if data in comes in and it's a 1, it toggles the value of the latch. So if the latch is a 0 and you toggle 1, it turns to a 1. If the latch is 1 and it toggles 1 again, then it changes to a 0. And then I have another thing called a repeater. And the repeater basically repeats the signal that's coming in, but with a programmable delay. And so if we go into then the encoder code, which is what happens first, you see that there's an in clock and a din. The out clock is nothing more than an observer that's watching the in clock line. And so then anytime the in clock line changes, it sends a pulse down. And then the D out is done a little differently. This little piece of code, and what this little piece of code does is it creates a rising edge every time there's a rising, it creates a single pulse every time there's a rising edge on the clock. And then I use that rising edge to mask data in. And so this thing is, we refer to it as a tertiary operator. It's an if-then statement. So if rising edge clock, which is this pulse that happens, ship down din, otherwise ship down all zeros. All right, so that's the encoder, and let's refer to the decoder. The decoder is a little more complicated. Let's scroll up. So what the decoder is doing is you've got an in clock, which is above the thing. There's the in clock. Let's recenter. You have the D and the out clock. So the in clock is coming in as pulses. The din is coming in as pulses. So I want to convert those pulses to levels. So one of the things I do is I take in the in clock and I look at this thing called valid values. And valid values is basically, hey, I look at the output of the T latch, which is what T-latch out basically comes in. Every time T-latch din changes, T-latch D out changes. What's T-latch din? T-latch din is this thing of basically data in, those pulse things, or a signal called reset latch. Reset latch is basically a thing that takes in the in clock, and anytime there's a T-latch D out, it says, oh, there's a value in the latch, therefore I must reset the latch on the next pulse that comes down in clock. And so you sort of see how this thing works. So now let's run the simulation. So I'll run the simulation by running Verilator on the top, and I have this thing called decoder tot, which includes both the encoder and the decoder. And I'm compiling it. And then the next thing I'm going to do is I'm going to run the simulation. So the first command created a binary. Now I'm going to run that binary. Now the binary has run. All right, so now I'm going to view it with the viewer. And so the previous command dumped the waveforms into this thing called dump.vcd. And here are all my signals. All right, now let's collapse this thing down. And so here we see the original data. I describe its levels. You've got data in coming in and changing every rising edge of clock. You have the encoded clock, which is a pulse in response to the edge changing, and as you see, it's delayed by a cycle. And then you have the data that's doing the same thing. It's pulsing, and you see that an E corresponds to an E that pulse, a Z corresponds to a Z that's pulse. And then we go to the output side, and you say, hey, here's my output clock. It's rising, and like I described, I want that rising edge happening at the same or after when the D out changes, and it's doing that. You see there's this low pulse of 0 for a single cycle at the end of the data thing. That doesn't matter because it doesn't get clocked in. The only thing that gets clocked in is what happens on the rising edge. And you see, woo, isn't that wonderful? Okay, but now that I've implemented logic and now that I've simulated it, you know what? I want to verify it by actually building this stuff in real life. And guess what? There's a real easy way for you to do that. And that, of course, is in Minecraft. So here we do. We have the thing. Down here, we have the encoder. And what this first part here is actually generating the data. And this section right here is actually the encoder. And then I'm sending these things down. Now you see why I'm sending things as pulses. Because in order to wire things side by side in Minecraft, you need to use rails. And the way that you send them is with observers on the rails. And so then you see the thing comes in as 2. It's going to reset. And then the next one will come in as 100. And on the left is the least significant bit. On the right is the most significant bit. So it went to 100. This thing down at the end is just counting. And this right here is the decoder, which is implementing all the logic of the decoder. And if we go out here, unfortunately, I sort of got bored and didn't try to get them all side by side. But here's the output. And the output is in the center. That's the lowest bit, the next, and then the most significant. And then this thing down here is the clock. And so you see when the light lights up, that's the clock rising. And then the data will change, and then the clock will rise. So there you go. I have fully implemented my design that I simulated in Verilog, and I pretty much knew that it was going to work, and I verified it working actually in Minecraft. Isn't that cool? Well, this is Yo Soy Bimbo Bob saying, don't be like me, like and subscribe.